Uh, yes, and as Nikhil mentioned, so this is a webinar that is going to be taking about 50 to 60 minutes. And it's going to be some couple of questions afterwards. Then I will explain about the course summary at the end of the session. So my name is Behzad Alayfar. I'm associate professor at NTNU, the Geoscience Department in Norway. So today I'm going to present the machine learning application for drilling engineering using Python. So here is a little bit of my background. So as you can see, I spent roughly about 2 decades in the drilling industry and also academia at the same time, working in different drilling topics and drilling scenarios. Now I'll try to put everything together to just combine it with the new technologies which we have nowadays, digitalization and machine learning and AI. So this presentation, I just split it into 3 sections: drilling measurements, machine learning techniques in drilling, and the machine learning application on real drilling data set is a case study. So normally when we're talking about the machine learning, we're talking about the drilling data. So first, I need to just go through, a couple of slides to show you where are these data coming from and how accurate they are. And based on that, we're going to start applying the machine learning techniques and those that we're discussing. So all in all, in general, the the drilling data that we're collecting from the operation is split into 2 parts: surface measurements and downhole measurements. Surface measurements, mainly link to all the equipments and the tools that we have on the rig floor. And we try to collect as much data as we can so that based on those information, we could just make a decision with respect to the couple of kilometers deep into the formation that we're drilling. So as you can see, all these data are going to be collected from different tools like mud pumps, drawworks, top drive, traveling block, and so on. Here I just listed some of these parameters that we are collecting, and you can add more, but I just listed some of them as an example for you. So just like flow rate, standpipe pressure, weight and beat, RPM, torque, return flow, ROP, beat depths, and so on. So these are the data that normally we collected at the rig floor. And based on these parameters, we are making decisions, we are making calculations with respect to the downhole. Sometimes, even collecting these parameters on the surface is not that accurate. So imagine that if you collect data which is not that accurate, and then you use that data to just do some calculation with respect to the downhole, then how would be the accuracy of the operation? So just as an example, you can see that some of these parameters where we are collecting them from. So like flow rate and the standpipe pressure coming from the mud pumps, weight on bit from drawers and deadline anchor, RPM and torque from top drive, the mud rheology, return flow, all these coming from the mud logging unit and storage, and the ROP and bit depths from traveling block. Just simple example. So for example, we measure torque from top drive, but again, the torque that we're measuring in the top drive, you already know that this torque is not the torque that is applied at the bit. So this is not related to that, because we have, depending on the depth that you have the driller string, which is, while rotation, it exerts some friction, and some part of this torque is going to be disputed along the string. So we need to just take into account that some of these parameters are not that accurate. It's we are looking for. So we need to implement some calculations up front. And then when you have all these data, when you collect them, then the question will be, what would be our analysis regarding the bottom hole condition? So as an example, one of the key parameters that we are monitoring all the time is ECD and bottom hole pressure. So ECD and bottom hole pressure, we need to calculate them. So the calculation is going to happen through pressure loss, hydrostatic head, all these formulas, but the input data is from the rig floor data collection. So in case if the mud window is wide enough we don't have that much of a problem. But in case if the mud window is narrow, then there is a problem here, because if the calculated ECD is not that accurate, then you might not be in the safe zone. Then the question is, okay, what we can do next? So, the next step, we need to bring some data from Downhole. So that would be good if we could just collect the data which are much closer to the action point, which is the drill bit. I listed some of the few equipments and tools that we have here, like PWD, MWD, LWD, and ASMs, which helping us to collect the data from Downhole. Some of the data that we are collecting, listed here, is just pressure, which in case if you have the PWD and ASMs, you can collect pressure inside and outside of the string, so in the annulus and inside the string. Temperature, the same inside the string and in the annulus. Vibration in 3 different directions, which is linked to the ASM. Inclination azimuths, which is linked to the MWD. Change in the weight and width and torque, which is linked to the ASM or EMS in case if you have it along the string. Resistivity, borehole images, neutron density, and so on. Even this is linked to the LWD. Depends how many logging tools that you're gonna install along your string. So all these sensors Downhole will help us to collect the data closer to the action points and increase the accuracy. So as an example, if PWD, which is coming behind it, and start collecting the pressure points, it is much more accurate for us than using the calculations from the data points that we are collecting from the rig floor. So why do we measure these Downhole measurements? Definitely we want to increase the accuracy, and by increasing the accuracy, we can optimize the operation, we can make a correct decision, especially when we are dealing with the directional drilling. Definitely it will help us to just hit the target more accurate, and also increasing the safety for sure. If all of our data points and calculations are more accurate, then the safety is going to increase. From pressure point perspective, we're going to be safely inside the mud window and we monitor everything. So this is, and then the main question coming up is that, okay, these tools and sensors are collecting data from Downhole, very good, but are we going to use them in the post-analysis and lesson learned section? So it means that we collect them, we store them, and bring them up and start analyzing this data, or are we going to use them in real time? So in real time, it is possible to use them. So in case if you have one of these communication system on board, like mud pulse telemetry, acoustic telemetry, electromagnetic telemetry, and wired pipe. So mud pulse telemetry is the one which is widely used around the world, and you have it almost in all offshore and onshore rigs. The good thing with the mud pulse, it's available everywhere, but it has some negative points. The bandwidth is not that high, so it means that the amount of information that you can transfer is not that high. And it also has some delays. Acoustic and electromagnetic telemetry, they're rarely used there for some special cases, but wired drill pipe, which is a new technology, I can say that at least in Norway, it is widely used nowadays. So operators are forcing the rig owners to just use wired drill pipe. And it's just like having the high-speed internet behind your bed. So you can communicate with Downhole real time per second, and also you can transfer tons of data. So that is helping us not even doing the post-analysis data, and also we can affect the operation in real time while dealing with these data. So up to this slide, I try to just give you a brief information of the data points that we are collecting from Downhole and surface, because that is the fundament for machine learning application. So next, let's start with the machine learning application and drilling data. So we know that the data that we are collecting, where are they coming from, how accurate they are, and how we can use them. Now let's apply the machine learning techniques for drilling data for the different purposes that we are looking for. So machine learning in drilling, integrating machine learning into drilling will, especially in the drilling industry, it will have a really significant evolution in the operation, both real-time and post-analysis. Real-time, with the machine learning techniques, we could, especially with data analytics, we can do the decision-making real-time, We can predicting the issues in real time. We can optimize the drilling parameters. And also definitely at the end, we're going to reduce the NPT, productive time. Post analysis, we finish the operation. Definitely every time after finishing the operation, we need to do lesson learned so that we can use them for the next operation. With the machine learning techniques, especially data analytics, we can just find out all these issues, even smaller, bigger one that we have in the operation, collect them, store them, and put them in the lesson learned scenarios, and we can use them in the future. And finally, it is using machine learning and AI will revolutionize the drilling operation, because nowadays most companies are looking for to have the operation. The first step is just do the operation remotely and going towards a fully automated operation, but that cannot be done really right way. So we need to do it step by step. So nowadays companies try to just automate different sequence of the operation and then connect, just like the application. So creating different applications and putting all these applications together in one platform and try to make the whole drilling operation fully automated and remotely from the office. We still need time to reach at that point, but I can see that at least, in Norway, most companies are, especially as all the operations in offshore. So everybody is, or most companies are focusing in this part. Good. Let's start to the core value, which is machine learning. So when we want to apply machine learning to the drilling data, especially I'm focusing on that one, for any purposes that you're looking for. I'm going to give you some examples. We go through it here. We need to just went through some of the steps, which is general. But then if you choose, for example, if you want to just create an ROP model, formation prediction, whatever scenarios that you're looking for with this, with the machine learning, you can use these steps one by one so that you achieve your goal. So the first step here is data collection. We need the raw data. So these raw data, as I mentioned before, we can collect them from rig floor, we can collect them from downhole. So depending on the accuracy and even depending on the availability, we can use them both. Next is descriptive statistics. So when you collect the data, then you need to, as an example, so we have, this drilling data, like, if you have ever been experienced with the mud logging unit data, you have, ROP, RPM, weights and bits, flow rate, mud density, viscosity, and so on, and many parameters we recorded. So let's say if you collected the data, the first thing that you need to do, you need to just do the descriptive statistics. You need to know that, okay, how many parameters are in my data collection or data set? How many data points are per parameter? What is the average value? What is the minimum? What is the maximum? What is the standard deviation? So all these need to be noted. I'm going to go through one case study following these steps afterwards, then you're going to see it in real time. The next step, which from my perspective, it's an optional step, is the data visualization. So what you can do when you got all your data, like ROP, RPM, flow rate, whatever, you can plot these parameters versus time or versus depth that you're collecting, and visually monitor them and see that, if there are any, deviation from the, data points. As an example, like RPM, when you start drilling a section, as an example, you started with 120 RPM. And then in midway, you increase it to 150 RPM and then finish it up that section. If you plot, RPM versus depth or versus time, then for that specified information, the only thing that you need to see is two straight line starting from 120 and then increase it up to 150. But in reality, you might see some other parameters or just other numbers inside, just like 1,500, 12, 10. So these are the noises, outliers, some values which in reality didn't happen. So we need to find them and we need to get rid of them. We need to filter the data, clean the data. One option is by doing the data visualization. That you can do, but if you want to put the whole machine learning process fully automated, then this step is not needed. So afterwards, we need to do feature analysis. So you collect all those parameters, I mean, ROP, weights and bit, flow rate, stuff. Let's assume that you're looking for, I mean, developing an ROP model, and you collected other parameters as well. But then you need to see that, okay, these parameters that I'm collecting, what are the impact of these parameters to my ROP? Some of them are having a great impact on ROP. By changing those parameters, the ROP will change. But some of these parameters that you're collecting on the rig floor, I mean, from different sensors, maybe have zero impact on ROP. By doing this, you can find out, okay, I mean, then I can eliminate and delete these, I mean, parameters which are not having any impact on the ROP or zero impact on ROP. Why? Because machine learning application, especially if you have a huge data set, is time consuming. So if you want to keep everything, I mean, in the system, your machine learning process is going to be more time consuming. So by this method, you can eliminate the parameters which are not directly impacting even the ROP for sure. Afterwards, after this, I mean, step, we will do data pre-processing, or what I call it, filtration. So in this case, we can start filtering the data. We can get rid of some outliers that are not related, I mean, into the operations that we can, I mean, I'm going to open up each of these boxes, I mean, later with an example. So we need to get rid of all those, I mean, outliers and noises and some missing values that, I mean, exist into our data set. Then afterwards, so when we want to implement the machine learning techniques, so we don't create some inaccurate models. After data pre-processing, then we will do the data splitting. So we might have some few data sets. Then we need to, for developing our model, we need to split them into two, I mean, data sets. One is for training purposes, which we need to train the model that we are looking for. And after we train our model, then we need to, I mean, do the testing. So when the model is trained, then we need to use the testing sets to just test the model to make sure that if the, I mean, model that we created is, I mean, having a good accuracy or not. So then the final step is model evaluation. So for any kind of, I mean, machine learning application, you can follow up these steps. And then depending what you're looking for, what is the goal, then you can easily do the implementation of the machine learning into drilling data that you have. So here, let's go through one example. So I try to bring one case study so that we can go through it together and understand what is happening. And throughout this process, I'm going to show you, I mean, the whole application with the Python coding. I'm going to bring the Python software, and we can see how, I mean, this process can be done. From the old days, I mean, most companies were looking for, I mean, the ROP model, as you can see here. Because if you have a good ROP model that can be helping you to drill, I mean, a formation, or even from the starting point to the end, then it's a win situation for you, because you can tune the drilling parameters and make sure that you have the highest ROP hitting the target. And that is, I mean, a really difficult task because ROP is depending on many parameters. Rate of penetration is dependent on weights and bits, RPM, flow rate, stamp-up pressure, mud weight, mud density, formation type, mud type, drill bit. I mean, a lot of parameters. So it is, I mean, the ROP is dependent on many functions that we need to bring it in. And even you cannot even use that model for the entire well. So you need to just attach it to the one formation. So I said that, okay, let's start developing an ROP model by applying machine learning techniques on the data that we have. So, but before doing that, I need to do some assumptions, because right now in 60 minutes, I cannot, I mean, go through all the, I mean, details. So I need to just make my example a little bit smaller. So let's assume that we are drilling in the same field. So the same field of the drilling in the North Sea as an example. And we need to zoom in again more. So we want to just drill, I mean, we need to collect the data of, I mean, few wells that is already drilled in the same field, and the data which is collected from the same geological formation. let's assume that as an example, we are just focusing on shale. So, I mean, shale layer or any layer, you can name it. So we try to just focusing, I mean, the same field and the same specified geological formation. And I'm just considering just input parameters. The input parameters are weights and bits, RPM, flow rate. These are the three parameters that the driller can directly impact. And also I added the standpipe pressure, which is some sort of a link to the flow rate. And definitely from upfront, I know that if I want to develop an ROP model using machine learning techniques with these four parameters, it's not going to be that accurate. But I mean, in the short time that we have, at least I can show you how this is going to work. So the objective, as I mentioned, apply machine learning techniques. I want to just develop an ROP model. The parameters that I'm going to work is weights and bit, RPM, flow rate, and the standpipe pressure. I have four wells from the same field. I mean, these data are real data. So 4 wells from the same field. The data are from the same specified formation. You can name it as formation A. Well, 1, 2, 3, 4. I mean, you can see the depth range 2200 to 3100, 2100 to 31, 3800 up to 4800, and so on. And even if you look at the mud density, you can see that they are much closer to each other. So 1.18 SG, specific gravity, 1.17, 1.21, 1.16. And you can see that the reason that is much higher than the rest is because the same formation was deeper for this well. So what we're trying to do here, because there are 4 wells, I'm trying to take 3 of these well data as data set for training so that I can train my ROP model. And then I'm going to use well number 4 for testing that model. And then when the model is good enough, and evaluated, see that, okay, the ROP model is good enough, then I'm going to use that model to drill the well number 5, which is not drilled yet, and apply that one for the well number 5 for that specified formation to increase the rate of penetration, optimize that one. And just be aware that if we increase the number of wells that we have, we're going to increase the accuracy of our models for sure. Let's assume that in this field, the plan is to drill 45 wells. Now we drill 4 wells. So if we got, let's say, instead of 4, we got 15 well data, we could have had a more accurate ROP model for sure. So for the example that I'm going to implement here, I might not be applying the last part, but in general, you need to be aware. So when you are building your ROP model, you need to just first bringing all the parameters that involved. And also you need to make sure that you put some boundary conditions. For example, when we have this drill bit, if you purchase a drill bit from any drilling service company, they will provide you with some limitations for RPM and also the weights and bit. So those limitations need to be applied here as well. And also you have a lot of other boundary condition. From pressure perspective, you need to have a pore pressure and frac pressure. So all these need to be taken care of as well. But I'm not going to apply for the example that I'm going to go through because we are focusing on just 4 parameters. It's not that much. So what was the first step? A data collection. Here is the screenshot of the data which I'm going to use, the real data. The first column is the column that I added. So I named them as well ID, so at least I can distinguish between well 1, 2, 3, 4. But then the second one is the hole depths, weights and bit, flow rate, standpipe pressure, RPM, and ROP. What I did, I put them inside an Excel file, and also, then I named the sheet and drilling data. So here is, as you can see, that I just put the screenshot there. And then if we go at the bottom, we have 3043, character, which if you remove the header, so we have 3042 data points per parameter. So that is, what at least I try to highlight, that we have these parameters, that I put it here. So this is the first step in the process. Next step, which is the descriptive statistics, is we need to just find out, okay, what are the the information that we got from those Excel files. So, I mean, if you can see in this, box, we have hole depth, weight and bit, flow rate, standpipe pressure, RPM, ROP, is the same information that I got in the Excel file. But what is the difference here is that we also went through the number of data points that we have per parameters. So it is 3042, exactly the one that we had in the Excel file. And we also got them in the average values, standard deviation, minimum, maximum. So to calculate, or at least to find out this information, we need a code. So what I did, I put the same codes inside the Python platform here for you. So let me see if I can. Oh, okay. Now it's really simple. So bringing in Panda library. So I'm not going to go through all the steps here. I'm just going to generally mention some of these codes, but because of the time, I cannot do that. But in case in the course, I can go through all these step by step. So I'm going to name or just call the data, which was inside an Excel file, and the same sheet that I put the name of drilling data. What I did here, I just dropped down the well ID column because I don't need to just put it in the descriptive analytics. And then you can name whatever you want. So I put descriptive status and the data.describe. So the data that we got is the Excel file, all the information here. And then if I run this code, then the result would be, the same that I showed you in the previous slide. If I go here. So it's the same, results that I got here. I just implemented and copy paste here. So then let's just go through these statistics. So we have, number of data points. We have the average value per parameter. We have a standard deviation. The standard deviation, indicates how these data are spread out. Especially from the average values. And it's really important. If the standard deviation is a low number, it shows that the majority of the data is spread in the mid part. And also we have, these 25%, 50%, and 75%, which we call them the Q1 quartile, Q2, and Q3. Again, these also show, how the data is spread. As an example, 25%. This is the value below which 25% of the data falls. And also it's a good indication of the lower end of the data that we have, how it is distributed. And the same for the 75% and 50%. 50%, is distribution in the mid part. 75% is in the upper end. So this is good because later we're going to use this to just start filtering data that we don't want. So this is the code that I already implemented into Python, and we got the results. Next, step, if you remember, was feature analysis. So feature analysis, what we do here, we try to find out, okay, now we want to just develop a ROP model, and we use 4 drilling parameters. We're going to see that what is the impact of each parameter to ROP. Now, for this example, it's not that serious, but in case if you have, if you use whatever data that you have on the rig floor and also downhole, then you need to just find out which parameters have a greater impact and which parameters has 0 impact. If it is 0 impact, you can just delete it because I mentioned before, it's time consuming. For doing this, we can use one of these 3 commonly methods. We need to use the correlation matrix. We're going to use either Pearson, Spearman, or Kendall-Style method for that one. Just a little bit of information on each of these. I'm not going to go deep into that. But for Pearson's correlation, it measures the strength and direction of the linear relationship between these 2 variables. And it is suitable for linear relationship. And if it is nonlinear, it's less effective. But in the other side, if you use Spearman's correlation, it is suitable for both linear and nonlinear version. And also you need to be aware of that the Kendall-Style is doing the same, but it is especially useful for small data sets that we want to use. If it is a huge data set, then the results might not be, I mean, that's what you're looking for. So, I mean, to do that, so we need to apply, I mean, this coding for finding out the impact of the parameters. Let me just bring my, okay, yes, Python. So for doing this, we need, I mean, on the library for data analytics, Seaborn and Matplotlib, to, because I'm going to draw, I mean, this heat map to show you the relationship between these, I mean, parameters. Again, we're going to read the data from the Excel file, the same sheet, and I'm going to drop down the well ID column. I'm not going to focus on that one. And then we're going to write down, we're going to calculate the Kendall style and Pearson and Spearman. We can name it, I just mentioned the Kendall's correlation or core, I mean, the rest, it's the data that we have and dot correlation, and then you need to write down the methods. It's Kendall, Pearson, and Spearman. And then afterwards, we're going to plot them. We need to plot the heat map for that one. The heat map for Kendall's correlation that we already defined on top. And I want to see the exact, I mean, you can get rid of these parts. Then you need to just look for the color coding. But if you add the end part, then you can have the color codings with the correct and accurate numbering as well. So if you run the code, the results would be, I mean, the heat map that we are looking for. I'm just going to bring you the results. So it's going to be looking like this. So let me just zoom in a little bit more. So what is showing in this Kendall style and heat map? It is ROP, RPM, standout pressure flow rates. I mean, both, I mean, X and Y axis. But then you're going to see that the impact of ROP and ROP is 1. So it's really strong. So it means that it is white almost, and the color coding is almost up to here. But then let's see what is the next. The next is what I can see here is the orange, which is the weight-on bit. So we know that ROP, weight-on bit has a great impact on ROP, because as you know, there is a direct relationship between the weight-on bit and ROP. So you increase the weight-on bit, the ROP is going to increase, but up to fundal point. So you cannot go above that one. But that is having a great impact. For this example, RPM is almost negative, so it's even less than 0. So it means that it has no impact on ROP here. But then, as this example, I mean, we're dealing with few parameters, I'm not going to eliminate anything, but in case if it's a huge data set, you can, if it is 0 or less than 0, you can eliminate that one. But you need to be, how do we say, we need to use your engineering, I mean, knowledge as well. We all know that the RPM has an impact on ROP. I mean, it might not be direct, but indirectly, because without RPM, there is no ROP. So, I mean, some of these, I mean, feedbacks may be linked to the data points that we have, I mean, the relationships. Good. This is the Kendall style. If I bring the other, I mean, graphs, this is for Pearson, different numbering, but the impacts are nearly the same. So the same pattern. So again, weight-on bit has a greater impact, but I mean, RPM. And also, I mean, the last one, which is the experiment. Good. So now we know at least which one has having a greater impact and which one has less impact onto the ROP that we are looking for. So we go to the next step. The next step is the data preprocessing, or we call it the filtration. So here, are we going to use interquartile range or IQR method to filter the data? With this method, we're going to measure or just look for the spread of the data in the 50% in the mid part. And to calculate the IQR, we need to calculate the 75 percentile or the Q3 minus 25th percentile, which is the Q1. So if we, the QR is going to be equal to Q3 minus Q1. And now we want to get rid of the much lower end, I mean, data points, which is lower than 25%, or they're much higher than 75%, I mean, in the upper bound. So if they're outside of this range, by using this method, we're going to chop them off and we're going to remove them from our data set. To do that, you need to use this formula, which is 1.5 times of the IQR, I mean, below Q1 or above the Q3. For doing that, And again, we can use the codes. In the code, I put it, if you can see, again, we're gonna bring the pandas, library. We're gonna go through the file that we have and drop down well ID. And then Q1 is equal to the data that we have multiplied by quantile 0.25, which is 25%. And then for the Q3 is 75%. IQR is Q3 minus Q1. The lower bound, which is less than 25%, is Q1 minus 1.5 times of IQR. For upper bound is Q3 plus 1.5 times of the IQR. So with this method, we can just cut out the data which are outside of this range, and we can delete them. And then we can filter the data. So we need the filtered data. So first we need to find out the data we don't need, and then take the one that we need. So the one that we don't need is the data which is lower than the lower bound, which is the 25%, or the data more than or above, upper bound. And then by adding this character, we're going to reverse the whole calculation. It means that instead of getting rid of those two, we're going to keep the middle version. And then we're going to save them in the filtered data. And then in the next step, what I did, I run the descriptive statistics after filtering to see that what is the difference between the descriptive statistics of filtered data and the raw data, to see that what's going to be the difference between them. So if you run this code, and then the result would be similar to what I put it here. So it is the same here. If you see, in the first or the raw data, when we did the descriptive, statistics, we had 3,042 data points. Now, after applying the filter, so now we have 2,025. So almost 1,000 data points were filtered out because they were in lower bound and upper bound. And then applying the mean, standard deviation, minimum, maximum, and also the average here. So by this method, you can start getting rid of the data which are not inside or outside of the lower and upper bound, which will helping you to just get rid of all those data that I mentioned at the beginning. As an example, if you have the RPM data, which should be around 120, 140, but now when you plot them, you're going to see that you have one data point or two data points, which is showing you 1,500, which normally we don't have an RPM of 1,500. And this one is in the upper bound, so it is more than 75%. Or maybe you have a data point for the RPM of 12, 13, 14, which in reality, we don't have that one. So those are much lower in the lower bound that you can just filter them here. Good. So when we do that, so now the data is filtered. Now we're going to reach to the point that we need to apply a machine learning technique. But then the question is, because we have different type of machine learning system, supervised learning, unsupervised, semi-supervised, or reinforcement learning. So here, what I'm going to do, I'm just going to put the focus on the supervised learning, because for us, at least, we know what we are looking for. It's the ROP, and we have the data, and we want to develop that model with the known data that we collected. So from that perspective, supervised learning is suitable for what we're trying to do for this example. But then the question is, which of these 10 methods I need to apply? To make it easier, what I'm trying to do, I'm trying to apply all these 10 methods to the data set that I have. And then we're going to compare the results, or compare the ROP model that we developed by each one, and see that which one is more accurate and which one is less accurate for these data points that we have until now. So let's go ahead, and then the next step was what we call it is the data splitting. So in the data splitting, we need, because we already know that we have 4 data sets. So well number 1, 2, 3. I'm gonna use those 3 well data for training purposes, and then I'm gonna use the well number 4 for testing, because we have the input data, weight and bit, RPM, flow rate, and the standpipe pressure. Look for the ROP model. 3 of these sets are going to be used to generate the ROP model, and then I'm going to test it with the well number 4 to see that if it is accurate or not. But then, if you remember, I mentioned I'm going to run all these 10 methods. But then I need to have some sort of a key metrics to just compare these methods with each other to see that which one is more accurate. For doing that, I need to do the error calculations. I need to do the mean absolute error, mean squared error, and R squared for each of these methods when I apply that one. And then by doing this, I can compare these methods with each other. Here I put a couple of slides to briefly describe each of these machine learning techniques. But the problem is, with this short time, I cannot even read through these notes. So what I did, I just already put the description here, and I know that this is going to be recorded and going to be uploaded on YouTube, so you can go through it afterwards. I put the references at the end, even you can look for that. But I'm just going to highlight some of the points, even not from all of them, with some of them, so you get some better idea, because the data set that I'm using is not that accurate, because I'm just putting the focus on 4 parameters. But if you want to apply with real data with many parameters, then you need to look for the best suitable method. For example, linear regression. It is widely used. It is simple. It is easy to interpret. Gradient boosting regressor. It is mighty for handling complex data set with interactions among variables. KNN is most effective for small data set. Rig regression, this method is beneficial when the data set contains many correlated predictors. The same with the others. If I want to zoom in or just highlight some of these points, for example, in the Gaussian process regression, it can be computationally intensive for the large data set. So you need to understand, first you need to see that, okay, how large my data set is, how many parameters do I have, which one is suitable. Decision tree, easy to interpret and understand, but likely overfitting. And also you can go through the rest. So you need to just go through, and when we talk about which one is more accurate, which one is less accurate, it depends on what you are looking for or what type of data set that you have, because each of these methods are really good and accurate for the correct data set that you're going to use. So, but we are in the drilling data field, and that depends on what you're going to do and what type of data you're going to use. So there is no, how do we say, there is no negative and positive method. So you need to know what you're using and what is your goal. What I'm trying to do here really quick, I'm just going to go through the linear regression really quick. So linear regression is a supervised machine learning algorithm which is used to predict a target variable, which is ROP, for us here in this example, based on one or more input variables, which is weight and bit, RPM, flow rate, and the relationship between these two are linear. So we're going to develop this linear equation. Y is the ROP, x1, x2, and xn are the parameters that we're going to input, and these are the coefficients, and this is the intercept. So to make it really simple so that you can understand, I give it 4 data points for 4 wells so that we can understand and go through. 3 of them are going to be used for training, 1 for testing. These are the steps that we're going to go through. Collect the data, split the data for training and testing, train it, and then test it. Here are the data sets that I developed. This is really an example that I generated these numbers, so it's not a real number. Well, 1, 2, 3, 4. So we're going to combine these data set together, and we're going to define features. X and target Y, ROP, and the rest. We're going to build a linear regression model, and then we're going to apply the model and test it, and then we're going to analyze the results. For doing that, what I did, I even write down the code for this simple example as well, so that when we run, then it's going to be much easier for you to understand. So let me just bring the platform again here. So NumPy library, and also I need to announce the linear regression library through the scalar. And then what I did, I defined well 1, well 2, well 3, 4 data points. and then I combine all these, data points which are in the simple matrix into one bigger matrix. And then we need to just create a feature matrix X for X train and Y train. X train, we know 4 parameters. Y train is the ROP, which we already defined up here. Inputting the, testing, the data. And then we need to create the X test, feature. And then we need to announce our model, or just call it. It's a linear regression. And then we fit the train, X train and Y train into our model, and then apply the predicted or the testing data set to just see that what will be the results. And if I run this one, the results here is looking like this. I go to the next slide. The equation, or the linear equation that we generated by the linear regression, is looking like this. So ROP is equal to this equation for these 4 parameters based on the data that we gave. And then we had the well number 4 as a testing, this one. So if you put, for example, 6, 1150, 80, and 140 into this formula, we're going to receive, ROP of 16.33. If we apply the rest, we're going to receive the other ROPs. And the real ROPs that I gave it to the system is this one. So you can see the difference between the predicted and the real one. That is how we, at least I tried to bring it in the lower level so that everybody could understand, at least mathematically. And the same process is going to happen when we run the rest. But then I cannot go through all these machine learning techniques right now in the short time, but in the course I will go through it. So let's go back to the ROP prediction model that we discussed. So before applying that one, what I did is that I try to just highlight, because we want to compare, these models with each other, or the machine learning techniques. To compare them, what we need to do is that we need to just make sure that the mean absolute error, mean squared error, and R squared is calculated. And we need to know a little bit of information about them. So mean absolute error is the difference between the actual and predicted value, and we're going to collect them all together. If the mean absolute error is 0, it means that there is 0 error and the model is perfect. But if it is more than 0, it means that you're having a distance from the perfect fit. The same with the mean squared. So if it is 0, perfect fit. If it is more than 0, so you're just distancing yourself or the model from a perfect fit. But for the last one, R squared, if it is 1, it's a perfect fit. It is 100% correct. But if it is less than 1, and if it distances from 1, it means that you're losing the accuracy. So we're going to use this tool to just see what is the which of these methods are going to be more accurate or not. Then this is the code that we're going to run. I put it here for you. So to apply all those 10 methods that we discussed for that data set that I showed you. So for doing this, we need to bring these on the library, and also we need to announce all these methods from the library as well. I already run the code because it will take 5 minutes to because it needs to train all those 10 models. But I'm going to go through it together, so we can go through it. So we need to bring all these the machine learning techniques from the libraries, and also some others because we need to plot them at the end. Then we need to announce where these data is located, where they are located, and then we start splitting into the training and testing data set: X train, X test, Y train, Y test. It's the ROP and also the other parameters. And then what I did, I created a small package, or a small dictionary, what they call it. All these machine learning techniques are collected inside this dictionary, a directory, what are you going to call it? Random forest, linear regression, regression, lasso. And then you need to have some tuning for each one. As an example, I'm not going to go in deep into each one, but for example, for random forest, you need to give them some n estimators. This 1000 is, for the random forest, is number of branches that you want to define so that it could start working. if you increase, I mean, from 1,000 to 5,000, 10,000, it will increase the accuracy. But at the same time, it will increase the, I mean, timing and timing analysis as well. So then you might be waiting a longer time. A random state, I mean, it just, if you put a zero, each time that you run the code, it will, I mean, give you the same answer, and so on. I mean, we're going to go through this, I mean, each of these methods in the course, I mean, afterwards. And then what I did, I named these methods one by one in this loop, and then apply the training data set, which I already defined on top, so that to just train my model. And then I start predicting or testing, running the testing, the data set into my model, and calculated R squared, mean absolute error, and mean squared error. When these are done, then I start, I mean, at the end, I plot them. So what I did, I plot the rate of penetration versus depth of the well number 4 that we put it aside as a testing data set. And then I also plot in the same graph all the other ROP predicted models, I mean, that these 10 models gave it to me. So, I mean, in the same graph, so we can at least visually see the difference, I mean, between the methods, to see that which method is just overlapping the ROP of the actual well, and which one is not. But then at the same time, I also printed out the results of the error calculation, R squared, mean absolute error, mean squared error, so that please we see which method, I mean, is having more accurate, I mean, than the others. But again, based on what we gave it to the system. So let me just, it will take 5 minutes. And now I got the results. Here is showing you the results of the actual ROP of the well number 4, which was used for testing purposes. As you can see, this black dot and black line is linked to the actual ROP, as you can see here. And the rest, which are just dots with different coloring, are all of the other methods that they applied, and they generate this ROP model and run the data of the well number 4. Yeah, some of them are good, and some of them, as you can see here, is really worse. So it's, I don't know, I mean, this should be SVR, I mean, it's really a straight line, and this is nonsense. So, and also we printed out this one. So if I go to the next slide, I just printed out the error calculations in this, I mean, box. Let me just come back here. So here, if you remember, I mentioned mean absolute error and mean squared error. If there is 0, it means that it's a perfect fit. But if it is more than 0, I mean, they're just, I mean, having some errors. But here, you can see that some of the numbers are small, some of them are really, I mean, big, and the same with here. For the R squared, the perfect fit was 1. 1 means it's 100% accurate. If it is not 1, it means that you're just going outside of the accuracy. And if you want to make it, I mean, easy to understand, if you multiply this column by 100, then you can see that you can at least name them by the percentage of the accuracy. For example, this one is 90% accurate. This one is 39% accurate, 39%, 40%, 39%, and this is 4%. So based on this table, the top 3 accurate models for my data set that I generated is random forest, decision tree, and AutoML. So you can see that, I mean, they're much higher than the rest. I mean, and these 2 numbers are much lower than the rest. So these 2 should be small, and R squared need to be high. And if you want to see that which models, or the 3 models with the least accuracy, then we need to look for them, and the ones which the R2 is small and these 2 are big. So it is linear regression, loss regression, and SPR, which are not, I mean, that accurate for this data set. And then this was the one that I showed you after running the code. Here, I just wanted to just show you the top 3 accurate models just separately. At least you can have a feeling that when we talk about the actual ROP model and the ROP model predicted by the decision tree is looking like this. The AutoML, and the random forest, which I think it is the accurate one. And also try to show you one of the worst one, which was, I mean, SVR, which this is absolutely not good. So I'm not saying that the method is not useful or really bad. The data set, or for the purpose that I was using, was not matching. So you need to be aware of that one. I need to go back here. Just be aware of that one, that these models that I generated is based on 4 parameters. Even I know upfront that the model is not good, it's not accurate, but I'm trying to just run through these methods to see which one is good or not. So if I want to wrap it up, so what we did today, we had 4 wells. We focused on one formation, a specific formation. It could be any formation. And we tried to develop the ROP model. So the data we collected from each of these wells, as you can see, some of them were deeper, some of them were not that deep and the same level, because, I mean, we're focusing on the same formation in the same field for 4 wells. And again, I mentioned, if you can collect, I mean, or you add more data points or parameters, you're going to increase the accuracy of the ROP model. And also, if you increase the number of wells, again, you're going to increase the ROP model, I mean, accuracy as well. So while drilling a new well, you can update your ROP model as well. So that could be done as well. But what we did today, we just used the machine learning to create an ROP model, I mean, for specified formation. What you can do, you can use it for different, I mean, purpose as well. So instead of ROP model, you can use the data for, I mean, formation prediction as well. So you can have, instead of just focusing on one formation and the data points related to that, you can collect the data of all these formations, like 1, 2, 3, 4, and with the drilling parameters for each one, and you can name them or give them a character, or just even name the formation that it is attached to that one. And then you can, again, just like the other one, categorize as training data set, testing data set, and then when the job is done and the model is created, you can apply that model to just start predicting the formations. Here is the end of my presentation. I hope that I could just manage it into, I mean, the right time. Just a couple of slides I just want to highlight. So this is a book, I mean, Digitalization, Python Application with Drilling and Geoscience Engineer, that I and my colleague Irfan Hosseini, we prepared that one a couple of years ago. And this is a book which is contain 7 chapters, all is 652 pages. From chapter 1 up to chapter 6, you start learning Python coding, I mean, from the basic, and also different libraries, I mean, NumPy, Matplotlib, and so on up to chapter 6. And all the examples inside this book is based on drilling and geoscience examples. So when you start learning Python coding from the beginning, all the examples and the case studies inside this book is purely mostly on drilling, which is, I can say that 80%, and the other 20% are from the other geoscience, I mean, knowledge like reservoir engineering, I mean, geophysics and others. And it contains many drilling examples. I mean, simple one like just how to develop a code or just write a code for hydrostatic head calculations, and then going upward to pressure loss calculations, trajectory design, managed pressure drilling, managed pressure cementing, well control stuff. And then in the last chapter, there were some few case studies which are real data. And it was applying machine learning and AI to the data. So formation prediction, ROP, I mean, prediction or ROP detection modeling, using the LWD, MWD data to predict, I mean, the porosity, permeability. All this stuff is, I mean, covered in the chapter 7. And as Nikhil mentioned, so there will be, I mean, a course, 2 weeks, I mean, 3 hours per day. What I'm gonna do, I'm gonna cover the whole book in these 10 days, and covering, I mean, the drilling, data measurements, data transmission and downhole measurements, basic coding, and then applying coding for different drilling calculations. I mean, algorithms related to drilling sequences like hydraulics, MPD, control mud level, CML, drilling problems, well control, trajectory design, managed pressure cementing, and so on. And in the second week, I'm going to spend time on the mainly machine learning techniques, all this stuff that I highlighted here, but because of time, I cannot go through them. And then when this is done, then it's almost what I can say in this book is about 100 to 150 coding packages of different problems included. So during the course, I can share all these codes with the participants. This is the reference that I collected, so you can, in case if you want, you can just go and check it out. And thank you, everyone. This is my email address in case if you have any questions related to this or even non-related to this, because at the university, I'm covering different drilling projects. You can contact me, we can have a chat and I can give you an answer. And as I know, I mean, at least in Norway, it's late. So some of you, maybe in the East Hemisphere, it's late for you. I'm ready to answer one question, but if you have more, please send me your